Good afternoon, ladies and gentlemen. First of all, I'd like to thank the organizers for inviting me for a plenary. That invitation came along with the topics already suggested, you see. And you realize that it is much more difficult to talk about the impact of control theory on society than any other technical talk. So I will do my best. I will present my personal views, of course. You may argue, and we all recognize that there are many ways how to approach such a subject.
Just a second. Do you hear well? Do you want the microphone? Is it okay like
that? I can even talk more loudly. Is this okay? Yeah, I feel better than handling the mic. Okay. Put it on. It works. So, first of all, control theory is an interdisciplinary branch of engineering and mathematics that deals with the behavior of systems with inputs. It's the briefest definition of control theory I'm aware of. And the objective of control theory is to alter the system's behavior so that it behaves in the way we like. Feedback control is the basic mechanism by which systems of all kinds maintain their equilibrium. Feedback control may be defined as the use of different signals, determined by comparing the actual values of system variables to their desired values as a means of controlling a system. So it's the general philosophy. First of all, however, we note that feedback exists in the nature. Conditions under which life can continue are narrow, in fact. A change in body temperature, let's say 0.5 degrees, is generally a sign of illness. The homeostasis of the body is maintained through the use of feedback control. And feedback control over long time periods is responsible for the evolution of species. So feedback is very important in the nature. And of course, people noticed. So there are man-made control systems as well. Feedback control is used by engineers so that the temperature in our homes stays within acceptable levels. Airplanes fly and maintain desired heading, speed, altitude. We control the emissions, and so on. In biomedical applications, electrical nerve signals are used to control prosthetics. Robots cut holes in bone for implanting artificial joints, and so on and so on. Even more, economic indicators such as unemployment and inflation are controlled by government fiscal decisions. It's very important to understand the major drivers for control theory. And I believe that to understand the impact of control theory on society, it is helpful to review these drivers of control theory development from the oldest times to the present and hopefully predict for the future. First, we know that the earliest examples of control were empirical feedback devices, very ingenious, but science lacking. They, however, responded to practical needs during any phase of human history. Gradually, however, science replaces the control art and supports new and even more exciting applications. So let's review some of the milestones of the development. Probably the oldest feedback mechanism on record is already a prehistoric one from Polynesia around 1600 BC. It's called the outrigger. And it was the need for improving roll stability of small canoes for people while exploring and migrating the Pacific Ocean. So they invented this. And the outrigger canoe racing is still popular these days, as you can see from the picture photo. In Europe, probably the oldest feedback device on record is the water clock of Ctesibios from Alexandria around 270 BC. It responded to the need for keeping accurate track of time, and at the same time, it gave rise to float valve regulators. Then, later, in the Middle Ages, the three brothers of Banu Musa in Baghdad, at the time, invented a water supply device, especially for cattle, which responded to the need for continuous water supply, and at the same time, this mechanism gave rise to the so-called on-off control system, very ingenious one. Then the incubator of Drebbel from Holland, 1620, where mercury was used to control the temperature inside the incubator, and it gave rise to the temperature regulators based on mercury first. A very famous pressure cooker of Papin from France gave rise to safety valves, for example. But I believe that by far the most famous control device originated during the Industrial Revolution, and is the centrifugal governor of Watt. It provided a very impressive demonstration of the action of feedback with the flying balls. So, let's review. The Asian history shows ingenious inventions where the control mechanism, feedback mechanism, we would say the controller, was not a separate system. It was an inherent part of the invention. It's very important to notice. But these feedback control devices have had an enormous impact on society throughout the history of mankind. Float valve regulators enabled keeping accurate track of time already in the antiquity. On-off control systems enabled continuous water supply in the Middle Ages. And the temperature regulators, safety valves, centrifugal governor, and so on, clearly marked the Industrial Revolution in Europe. So now we come to the so-called modern age, which is characterized by the transition from intuition to science. No theory was backing the early devices using feedback. Automatic control was empirical, simply. The centrifugal governor, however, drew attention of scientists and gave rise to systematic study of systems and control. By the way, it was Maxwell who first did the stability analysis of a system governed by this centrifugal governor. So Maxwell not only put together the equations for the electromagnetic field, but he can also be considered the father of automatic control. From that time on, control theory was based on mathematical models, very simple at the beginning. Control devices started to be gradually replaced by universal controllers, a box, let's say, making no longer an integral part of the inventions. Here are some milestones of the modern age development. First of all is the stability analysis by Maxwell and mainly by Lyapunov. The invention of feedback amplifiers, especially negative feedback amplifiers, by Black, and the analysis provided by Nyquist, you see. PID controllers invented by Minorsky, or at least described by Minorsky for the first time, with the famous tuning rule still in use by Ziegler and Nichols. Then optimal control after the Second World War, marked by the contributions of Bellman, Pontryagin, and also Kalman. Then we And now we are in the computer age. Computer technology represents certainly the most significant technology of the 20th century. Significant revolution. It has had a significant impact on control theory itself, as well as on control systems implementation. Computers undoubtedly enabled unprecedented developments in communications, and control systems are simply omnipresent these days. Let's review the past trends in control theory in more detail. There were analytic methods at the beginning. See the analysis of Maxwell, the stability theory of Lyapunov, and so on. And they gradually started giving way to computer-based solutions. In the 40s, for example, problems were considered solved when a closed-form solution was found. This closed-form solution formula was then used in both analysis and synthesis. For example, Wiener formula for optimal filtering. Later, say in the 60s, governing equations were derived, but an algorithmic solution was left to a computer. For example, Kalman filtering equation, Riccati equation of an optimal control. So the Riccati equation was still used for the analysis, to certify the existence of solutions, to help us to understand the problem. But its solution was left to MATLAB. Now, problems are considered solved when mathematical programs are set up. And both the analysis and synthesis are replaced by computer-aided design, like linear programs, quadratic, semi-definite, and so on, programs, especially in robust control. So you see the graduate shift from analytical to computer-based methods. And what can we predict for the future? Certainly, control theory is looking for new solutions to address the control of complex systems, or as we say, systems of systems. Typically, distributed control over communication networks, or real-time control with reconfigurable systems, various hybrid control systems, and collaborative control or agent-based control. We can sense in these problems a strong influence of computer science. We see that traditional model-based methods are gradually replaced, but not completely, by knowledge-based methods. And what are the corresponding trends in applications? I believe that control theory is a key facilitator of the modern technological developments. First of all, with impact on the product performance. Clearly, in general, we can say that performance improves, costs decline, reliability and safety increase, energy consumption decreases, or we could say that impossible becomes doable. But control theory is a key facilitator not only as well as the performance is concerned, but also it has a great impact on the product range. Control is expanding to every fields: manufacturing, transportation, energy efficient buildings, medicine, machine interaction, and so on, including life sciences. So let's go one by one. Manufacturing and processes. I believe that future manufacturing will be highly automated. We shall see unmanned factories and processing plants. The so-called plant-wide automation including everything, including the decision processes, will take engineering as well as economic and environmental criteria into account. And for these purposes, hybrid control systems will have to be studied to meet all these requirements, of course. Transportation and vehicles. The traffic density is high, yet the safety situation is still not satisfactory. That's what I believe. So we have to develop advanced driver assistance systems, especially with focus on to solve the critical situations for the driver. And when combined with infrastructure improvements, these will yield intelligent traffic control, both on roads as well as rails. And the autonomous unmanned vehicles, it's a special category, of course. They are used for like drones, like robots. They are used for situations such as operation in hostile environments for every reasons. Buildings are complex systems composed of many subsystems. So this is a good example of systems of systems. These subsystems were traditionally deployed independently of each other. And this applies not only to building energy systems like heating or cooling and so on, but also to access control, fire protection, surveillance, and so on. Real-time control and optimization can help building owners and tenants to minimize energy consumption and cost. Here, of course, the challenges for implementation of advanced control solutions include the heterogeneity, complexity, and disturbances. Medicine, we all know that. Medicine and human well-being. Control mechanisms and control systems are used to restore lost functions to paralyzed individuals, for example, using feedback control of electrical stimulation systems. Robots are used in medical interventions. Control of advanced diagnostic and therapeutic instruments of the modern time can hardly be imagined without sophisticated algorithms. Even feedback control is possible using eye movements of people to enable handicapped persons to operate machines, for example. When I look like this or this, okay, the machine will do different things. And control functions will be embedded in all everyday functions in the future. A very nice example from this area is the control for the artificial pancreas. The human body uses opposing manipulated variables to achieve regulation of blood sugar, much the same way as the driver uses the brake and gas pedal. So insulin, which is the brake pedal, and glucagon, which is the gas pedal, are both produced by the pancreas. So the artificial pancreas system is a fully automated device with blood glucose monitoring at a sampling rate of several minutes, every few minutes, and dual chamber pumps to deliver both insulin and glucagon equipped with model predictive control algorithms. Man-machine interactions. People will have to collaborate with robots. So there must be a way of interaction, of understanding each other. So we have to study voice systems for man-machine interaction with the final goal to achieve communication with machines in the natural language. Machine perception and image analysis are used in object detection, recognition, localization, and so on. And we have to prepare the teams of humans and robots working together. These robots will have to localize themselves, will have to avoid damage. We will have to have some measures to to provide detection of failures in decision making, and even how to manage the handover of control from the robot to a human operator. Now communications are used in control. An example is control over communication networks. The constraints imposed by the communication channels are very hard and include, for example, a limited bandwidth, various delays of variable amount, quantization errors, transmission noise, and even worse, random loss of information. And the prediction is that the worldwide broadband network will prove to be the most significant revolution of the 21st century, just like the computers were in the 20th century. Oh, no, too much. Okay, communications in control. On the other hand, control is alive also in communications, the other way. Mobile telecommunications technology is having an unprecedented impact on human society. We all have mobile phones ready all the time. The successful operation of modern communication systems depends in part on highly sophisticated real-time control. The inner loop power control used to adjust the signal to reference ratios of users at the base station. Another example is the outer loop power control, which is used to adjust the block error rate, and especially the tasks of scheduling in the future 3G and 4G systems will allow for high uplink data rates between the user and the database and the base station. Now we come to economy. This is an example of a large-scale, strongly interconnected system. The national economy, each national economy, is a part of the world economy with many agents. Even more, humans are included in the economic loop, which complicates the control. And billions of euros, or dollars, of Czech crowns, whatever, are at stake. And livelihoods of families are also at stake. The complexity is simply overwhelming the managers. And we will have to decide what is the right architecture for data sensing, communication, and control in such large-scale and strongly interconnected systems. As an example, Jean Tirole, the Nobel Prize winner 2014, clarified how to regulate industries with only a few powerful firms. Well, left unregulated, such markets often produce socially undesirable results. And he noticed that general policies for all industries are no good. The best regulation policies are industry-specific. And drawing on these new insights, he suggested how the governments can better encourage powerful firms to become more productive on the one side, and at the same time prevent them from harming competitors and customers, let's say, too much. Life sciences link complex systems with architectural demands, and especially with application-specific demands. We have witnessed the biotechnology revolution, which forced many biologists to understand issues of system theory and feedback control, for example, and vice versa, of course. Biological structures and capabilities may inspire mimicry. We might learn a lot from the nature. And especially, we should realize that nature has not done any analytic design, but it has produced brilliant iterative designs instead. Can we shift our thinking to do the same? So, which future developments I can see and predict? First of all is the ubiquitous availability of computers, which will facilitate continuous automatic control of everyday functions in our life. We know that control is everywhere in reality, but it is also nowhere in perception. Simply, control remains a hidden technology. If a control system works well, nobody notices. Control and computer technology will enable many new consumer products and foster new perspectives for work and business. And for this, need for workforce educated to unprecedented levels of scientific and technological expertise will be great. So let me conclude simply. I hope I have persuaded you that the impact of control theory on society is great, both in size and in degree. Second, that control theory is a key facilitator of the modern technological developments. Control systems are hidden yet omnipresent. And what I consider most important is the marriage of control, information, and communications theory as an important intellectual driver for the future. Here are my references and credits. Thank you very much for your attention.
Thank you. We have plenty of time for questions, discussions, comments. I'm sure we all have points of view on the impact of control.
Yes, it's a change from standard technical talks.
My feeling is that we do have a need to convince people outside our community of how important control is. You know, or believe it is.
Especially if it is hidden.
But it's hard to explain.
Yes. Yeah? Yes. Control community grows, but some other communities like ICT and so on grows even faster. You know, so we are under more pressure. And what's important, the computers, telecommunications not only make the applications possible and easier, but they, like feedback, influence the theory itself, as I wanted to explain how the analytic methods are gradually displaced by other kinds of computer-intensive techniques.
Michael.
You mentioned that one of the fields that's changing the fastest, of course, as we all know, is biology. And you mentioned that biologists are having to learn control. Could you maybe expand on that? I mean, how much is that being used in biology? How much is control playing a part in modern biology?
Okay. What I had in mind when preparing this part of my lecture, I recalled what actually is called cybernetics. Cybernetics, as defined, let's say, by Wiener, or maybe even others at the time, he just coined the name for it, I believe. Anyway, it was, the idea was to copy what we see in the nature, in living mechanisms, in living bodies, and to do it ourselves as engineers. You know, so then, therefore, we have to learn mutually. We are influenced and motivated by what we see around, by behaviors in humans and living bodies, and we try to design our engineering systems accordingly. For example, when I want to grasp this, you know, my hand goes fast first, and then somehow touches, let's say, quite softly, you know, the object. So it's a beautiful example of control, okay? And such things are to be learned and copied. let's say, by engineers. And on the other hand, I mentioned that the biologists started to think in terms of systems. So this means decomposing complex events and complex phenomena into smaller pieces and to study them separately and then in interconnection, which is typical for systems approach. That is what I had in mind.
Thank you very much for that presentation. I have two questions. What is new in the control structure development?
Control structure.
There are several combination, modification of control structure, for example, plant-wide structure for the industrial application. What do you think about this, choosing the optimal control structure?
Yeah, this is very important when we handle increasingly more complicated, complex systems. Because the control of simple systems is already done. So now we go to more and more complex systems, and the interconnections and the control architecture, okay, becomes more and more important. So we noticed already several decades ago when consider hierarchical control, for example. That's one good example. No? But then in living mechanisms, in tissues and so on, we find still different architectures between neurons which might inspire us for mimicry. That's the structure.
What do you think about this implementation of advanced control algorithm method using the chip? Because there exists a lot of application, for example, model predictive control, which are implemented on the chip, as a chip.
On chips?
Chips.
Uh-huh.
Chips.
Yes. Because of the advances in computer hardware and software, our computers becomes as small as chips. So they are still more powerful. So we can implement more and more advanced algorithms, which was not possible 50 years ago. The chips may be even embedded to humans, to animals, else everywhere. And that's one way how to achieve the automatic control of many everyday functions we have. So I think that this is quite natural, and it is facilitated by the advances in hardware and software development.
I think this is a new trend.
Yes, it's a new trend, yes. Because such a chip is like computer. First we had a big hall and we set up a big computer there, okay? Some 50 people were running around, keeping it to work. Now we have small chips, as small as they can be implanted to parts of our body, and do much more interesting functions than it used to be before. And just imagine, only more than half a century, slightly more than half a century elapsed between these two times.
Thank you.
More comments, questions? I'll take a short 2 minutes then to, well, it's related anyhow, to say another word about Ifac 2017. So, every 3 years we have the Ifac World Congress, next time in Toulouse in 2017. And we just released the call for papers. Few people know about it because it seems very far from the deadline, but it starts to be interesting. And we have two new sort of features in there. We could have submissions that would be dedicated to the history of control. There's one. We could because we'll celebrate the 60th anniversary of Ifac. So the idea here is to submit papers that will be peer-reviewed, talking about history of control. So if you have something in mind, please think about it. As 1 year of paper, I'm sure some people could have brilliant ideas about that. The second one is a demonstrator paper. The idea is to illustrate a lot of old Vladimir told that control is everywhere, but it's very difficult to explain that it's everywhere, because usually we'll show that on the slide. For us control people, we understand immediately what control problem is behind, or maybe not immediately, but we can understand that, but the public doesn't. And so the idea here is to invite contributors, researchers from the industry as well, to bring some prototypes, some demonstrators from the labs, to really show how we concretely do control on demonstrators and demonstrate the reality of control. It would be both interesting, I think, for the participants of the World Ifac, and we'll have sort of exhibitions of these demonstrators open to the public during the conference, trying to show what we're doing, not only to ourselves. So think about that also. It's, in terms of logistics, more complicated, but if you have a nice demonstrator, or know people having nice demonstrators, well, incite them to submit something talking about that and bringing the demonstrator.
Sure.
Little advertisement, sorry.
That will be a great event in Toulouse.
Any more questions arise? Yeah, sure.
Going back to what we said with control being a hidden technology, how do we go about fixing this issue? We know the industry is not unwilling to move forward. They still cling on to PID and MPC. How do we convince them, even though they know what advanced control is, what some people would call advanced control, like agent clinical control, how would we convince them that they need to do this?
Yes, I'm sure that the good companies, they know what the advanced control is, but their problem is maximum safety. They must be 100% safety. And maybe MPC control is only 99.99% safety. That's the problem. It takes a long time. It's generally believed that from invention to application, it's at least 50 years. That's normal. The nature, okay, prevents us to progress too fast, simply. Yeah, we have to. They will, I think we theoreticians are not able to persuade the companies. They will be persuaded by cases, okay, successful cases. And they will take it up very slowly and very cautiously. For example, the model predictive control already mentioned is one of the few examples that replaces indeed the PID controllers in chemical processes because of the special nature of chemical processes mainly. Okay? And there are other areas in modern control. It's much more difficult to use the advanced control, for example, in airplanes. No? But let's say maybe to control the drones, okay, they can test it. And then Airbus will take it. We ourselves will be more comfortable when seeing well-proven controllers inside. Okay.
More questions, reactions?
In the early days of
I'm sorry.
You mentioned in the early days of Norbert Wiener that cybernetics was really the father of control in some sense, yes? But actually control broke away from cybernetics. You could view it in that,
No,
that sort of way.
I
Do
hope.
you think there was a lot to be gained from the control community by breaking away from cybernetics in the 1950s, 60s, I would say?
Yes.
The time of the beginning of Ifac.
I use cybernetics only as an example that people can learn from the nature and try to do the same. That happened, let's say, in the 40s or 50s. But as I tried to convince you, control theory started to exist many years ago, before that. Okay? So control theory and cybernetics are two different things. But control theory before the Second World War was industrial based. Okay, PID weapons also. Yes, so anti-human, not human. So the power of these patterns, which we can see in living mechanisms, okay, that's still an idea we pursue these days, I believe. We may not call it cybernetics, okay? It depends on the taste. Some people like cybernetics, some people don't. But in any case, cybernetics developed into several self-contained disciplines, including automatic control. Yeah. And control theory these days is a sort of applied mathematics. We have to admit that. Okay? As opposed to it, we have control engineering, which is not applied mathematics. And this creates the so-called famous gap. And I believe that thanks to that gap, we go forward. So this is one of our drivers. If it were no gap, we would be sitting here and doing nothing. So thanks to the gap, okay, we have.
Thank you. Turan Söylemez from Istanbul Technical University. Actually, from my perspective, I see people who are dealing with control engineering in three categories. I don't know if you would agree with me. In one category, there are theoreticians who do lots of theory and know the stuff in a high manner. And in the other end, we have application-oriented people. They are actually on the business. They do all the control work for the industry, but probably they do not like theory that much. When you talk to them in terms of Laplace theory or some other theories, they are a little bit afraid. And in the third category, what I would call as translators. So they somehow put that theory and then formulate basic formulas for those who are in the industry. As I can see, this third category, the people who are working in this third category are not that many. I don't know if you would agree with me, and what's your perspective on this issue?
Yes, sure, I agree. I do agree with you. I was talking about theoreticians and practitioners as the two poles. But of course, the community is spread more or less evenly between. Even the theoreticians hope the result will be applied by another theoretician, or hopefully by some practitioner. Okay? And even the practitioner would be happy to justify his results to say that he was using some piece of control theory. And as you say, the translators or mediators, okay, in between, they are very important, because it's the most difficult thing is to understand each other. Okay? Theoreticians speaking to a practitioner, okay, sometimes have no common language. And it takes some time to understand each other, and only then they can start effectively working together. So this is very difficult. That's why there are not so many, probably, and it's very important. Sure, I do agree.
Some more comments, questions? Oh, wow, it was good. Thank you, Vladimir. Thank you to everybody.
Thank you very much. Thank you. And thank you, Dimitri. Thank you.